3.8 million miles from Earth, something is moving through the outer atmosphere of the Sun that no instrument built by human hands was ever supposed to survive. It is not a satellite in the way you imagine satellites. It is not orbiting safely. It is not watching from a distance. It is inside the corona, the searing, ghost-white halo of plasma that surrounds our star, a place where temperatures climb past 2 million degrees and the laws of physics themselves seem to bend. And on its most recent pass, it sent back data that NASA's own scientists are still trying to explain, because hidden inside the Sun's atmosphere, woven into the chaos of charged particles and twisted magnetic fields, Parker Solar Probe found something that, according to every model we have built for the last 60 years, should not be there. A barrier. Not a wall of matter, not a structure you could touch, but a real, measurable physical boundary inside the most violent environment in our solar system, a place where energy itself stops behaving the way energy is supposed to behave. And the strangest part is not that it exists. The strangest part is what it might be doing to us. To understand why this matters, you have to understand what Parker Solar Probe is, and why nothing like it has ever existed before. When NASA launched Parker in August of 2018, the engineers behind the project told the world the mission was, in their own words, impossible, not difficult. Impossible. Because to fly into the Sun's atmosphere, you have to do something no human-built object had ever done. You have to survive temperatures hot enough to vaporize steel. You have to maintain a stable trajectory at speeds approaching 500,000 miles per hour. You have to communicate with Earth across a sea of radiation that scrambles signals and burns electronics in seconds. And you have to do all of it while a heat shield just 4.5 inches thick holds back the full fury of the closest star to our planet. For decades this mission was theoretical, a dream, a line item buried in NASA budget proposals that always got cut. The materials didn't exist. The shielding didn't exist. The math wasn't even fully understood, and yet on December 24, 2024, Parker Solar Probe did what no spacecraft in history had ever done. It flew just 3.8 million miles from the surface of the Sun. It moved at 430,000 miles per hour, fast enough to circle the Earth in about 3 minutes. And it survived. 8 days later, NASA received a signal. The spacecraft was alive. The data was intact, and what came back changed solar physics overnight. But that was only the beginning. Because Parker has done it again. And again. And again. On June 19, 2025, the spacecraft completed its 24th close approach. On September 15th, its 25th. On December 13th, its 26th. And on March 11th, 2026, it completed its 27th once again, sliding to within 3.8 million miles of the Sun's surface, gathering measurements no human had ever recorded from the inside of a star's atmosphere. Every pass returns a torrent of new information. Every pass forces scientists to rewrite something they thought they understood, and one of those passes returned something that no one was looking for. A barrier. Inside the Sun. A barrier that no theoretical model predicted, that no instrument before Parker could ever have detected, and that if confirmed would explain a mystery that has tormented solar physicists for more than 6 decades. But to understand why this discovery is so disturbing, you have to understand the question it answers. In 1939, a Swedish astronomer named Bengt Edlund made an observation that should have been impossible. He was studying spectral lines in the Sun's corona, the faint outer atmosphere visible only during a total solar eclipse, and he found signatures of iron atoms that had been stripped of 13 of their electrons. To ionize iron that aggressively, you need temperatures of around 2 million degrees Celsius. That was a problem. Because the Sun's surface, the bright disk you can see during the day, has a temperature of about 5,500 degrees Celsius. Hot enough to vaporize anything we know. Hot enough to make life on Earth possible, but nowhere near 2 million. Which meant that as you travelled away from the sun's surface, moving outward into space, into the thinning, ghostly corona, the temperature was not falling. It was rising, hundreds of times higher. This violated everything we thought we knew about heat, about thermodynamics, about how energy moves. A pot of water on a stove does not get hotter as you move away from the burner. A campfire does not get hotter the farther you stand from it. Heat flows from hot to cold. That is the most basic rule in physics. And yet, somehow, the sun was breaking it. For 60 years, this question, the coronal heating problem, has been one of the most famous unsolved mysteries in modern science. Entire careers have been built around it. Billions of dollars have been spent chasing it. Telescopes on every continent, satellites in every orbit, and decades of computer simulations have all tried to answer the same question. How is the sun's atmosphere hotter than its surface? Theories came and went. Some scientists believed in waves' magnetic vibrations rippling up from the surface, dumping their energy into the corona like ocean waves crashing on a beach. Others believed in flares, tiny, constant explosions called nanoflares, too small to see individually but powerful enough collectively to heat the entire atmosphere. Others still believed in turbulence, the chaotic churning of plasma, transferring kinetic energy into heat. For decades, every theory had supporters. None of them had proof. Because to prove any of them, you had to do something no instrument could do. You had to go inside the corona and measure what was happening there. Directly. And until December of 2024, no human-built object had ever been inside the corona long enough to find out. But Parker had. And what Parker measured was not what anyone expected. The data came back in waves. Literally, because what Parker was detecting, as it cut through the sun's atmosphere at 500,000 miles per hour, was not a smooth, calm flow of plasma. It was something far stranger. Something more alive. The solar wind, that constant stream of charged particles flowing outward from the sun, was not flowing the way physicists had assumed. It was full of switchbacks. Sudden, violent zigzags in the magnetic field, like a river that abruptly reverses course and then snaps back into place. These switchbacks were everywhere, tangled, folded, some of them so sharp that the magnetic field bent more than 180 degrees in less than a second. This alone was a discovery. Switchbacks had been spotted decades earlier by the Ulysses mission, but Parker showed they weren't rare anomalies, they were everywhere. They were fundamental. And here's the part that started to feel uncomfortable. The switchbacks weren't just structural curiosities, they were energetic. They carried enormous amounts of magnetic energy with them, and that energy was being released somehow into the surrounding plasma. For a while, scientists thought they had found their answer. The switchbacks must be the engine. They must be the long-hidden source of coronal heating. The mystery after 60 years must finally be solved. But the deeper Parker went, the more the data started to argue with itself. Because the switchbacks weren't depositing enough energy in the right places, the numbers didn't add up. By 2024, a team at the University of Michigan had run the calculations and confirmed it. The S-shaped bends in the sun's magnetic field could not, on their own, account for the temperatures observed in the corona. The mystery was still alive. And it was about to get worse, because hidden in the data buried beneath thousands of hours of telemetry was a signal no one was searching for. A signal that suggested the energy in the corona wasn't just being deposited inefficiently, it was being blocked by something invisible. In the summer of 2025, a paper appeared in the journal Physical Review X. It was published by a small team of researchers led by scientists at Queen Mary University of London, working in close collaboration with NASA. The title was technical, the language was dense, and the implications were enormous. The paper described, for the first time using direct measurements from inside the corona, evidence for something physicists had only hypothesized about for years. They called it the Helicity Barrier. To understand what that means, you have to picture what is actually happening in the sun's atmosphere. The corona is not empty space. It is filled with plasma superheated electrically charged gas, and that plasma is constantly churning, twisting, tangling. The magnetic field threading through it carries energy from the sun's surface outward into space. As that energy flows outward, it is supposed to do two things. It is supposed to accelerate the solar wind, and it is supposed to dissipate, dumping its remaining energy into the surrounding plasma as heat. That second part was the missing puzzle piece, the mechanism by which energy in the magnetic field becomes heat in the plasma. And what the Parker data revealed was that this transfer doesn't happen smoothly. It hits a wall. Under certain conditions, when the magnetic field becomes strong relative to the pressure of the surrounding gas energy in the system, can no longer cascade down to the small scales where it would normally turn into heat. It piles up, it accumulates, it builds. The barrier doesn't stop the energy, it traps it. And once trapped, that energy has to go somewhere. What Parker found is that it goes into a narrow band of frequencies, where it heats certain particles' ions in particular to extreme temperatures. Other particles are left relatively cool. The corona, instead of being uniformly heated, becomes a strange asymmetric environment, where some species of plasma are blasted to millions of degrees, while others remain comparatively calm. This is not how the textbooks describe it. This is not how the simulations predicted it. This is something new. And here's what makes it disturbing. The Helicity Barrier is not a static feature. It comes and goes. It strengthens and weakens depending on conditions in the solar wind, and when it forms, it changes the way the entire system behaves, including the speed and composition of the wind that eventually reaches Earth. Which means the barrier isn't just a curiosity inside the sun, it might be shaping the space weather that hits our planet. If you're following this and you're already starting to feel the weight of what's being uncovered out there, that quiet sense of, why isn't this on the news, consider subscribing. We track these stories week after week, and they are accelerating. The sun in 2026 is not the sun your science teachers described. Now let's go deeper. The discovery of the Helicity Barrier does not just solve, or partially solve, the coronal heating mystery. It rewrites our understanding of how stars work. Because the sun is not unique. Every star in the universe has an atmosphere. Every star generates a stellar wind. And the mechanisms Parker is uncovering in our own sun almost certainly operate in other stars too, including stars whose planets we are now studying in the hunt for life. The energy that flows outward from a star shapes everything around it. It strips atmospheres from planets too close. It seeds the chemistry of planets at the right distance. It defines the habitable zone. It defines what biology, if it exists out there, has to survive against. If the Helicity Barrier is universal, if it operates in every star with a magnetic field, then every model we have built of stellar evolution, every estimate of how solar winds shape young planets, every prediction about habitability has been built on incomplete physics. That is the scientific weight of this discovery. But there is also a more immediate weight, one that lives much closer to home, because the same barrier that traps energy inside the corona also influences the violence of what the sun sends out toward us. And we are entering a moment in solar history when that violence is starting to escalate. In late 2024, NASA and NOAA jointly announced that the sun had entered the maximum phase of solar cycle 25. This was the peak, the high point of an 11-year cycle of solar activity that had been building since 2019. For most of human history, solar maximum was an invisible event. A few extra sunspots, a few more auroras at high latitudes, nothing most people would notice. But in the 21st century, solar maximum is different. Because everything we depend on now is electronic, power grids, satellites, GPs, banking systems, aviation, communications, every part of modern life runs on infrastructure that is, by physics, vulnerable to large-scale geomagnetic disturbance. And the sun, in this cycle, has been more active than the forecasts predicted. In May of 2024, before the formal announcement of solar maximum, a series of intense solar flares produced one of the strongest geomagnetic storms in 2 decades. Auroras were visible as far south as Mexico. Power systems experienced fluctuations, satellite operators reported anomalies, SpaceX lost dozens of Starlink satellites that had been launched into low Earth orbit, dragged down by an inflated atmosphere caused by the storm's energy. In May of 2025, the Sun produced an X2.7 flare, the strongest of that year up to that point. In November of 2025, the European Space Agency tracked a major space weather event triggered by an intense solar flare and an Earth-directed coronal mass ejection. Their teams issued alerts across the European infrastructure community. On December 8, 2025, NASA's Solar Dynamics Observatory recorded another strong flare. Then came the new year, and the activity didn't subside. On January 18, 2026, the European Space Agency released composite imagery of an X-class flare and its associated coronal mass ejection blasted outward from the Sun's western limb. And on February 4, 2026, an X4.2 flare erupted from active region 4366 Earth directed. Solar cycle 25 was supposed to be a weak cycle. That was the official forecast. NOAA's prediction panel, back in 2019, projected that the peak sunspot number would reach somewhere around 115, comparable to the previous cycle, which was itself weaker than average. The actual numbers have not behaved that way. The cycle has been more energetic than the model predicted. And the tail of the maximum, the long decline that should now be underway, is producing flares and coronal mass ejections at a pace that frankly surprised even the scientists tracking it. Which raises a question Parker Solar Probe is now uniquely positioned to answer. Are these escalating eruptions connected to the Helicity Barrier? Officially, no one has confirmed a direct mechanistic link. That has to be said plainly. Solar physics is a slow, careful field, and the Helicity Barrier paper was published less than a year before this script was written. Connecting it to specific space weather events is still, at this stage, an open scientific question. But the line of investigation is there. The Helicity Barrier influences how energy moves through the corona. The corona is the launching ground for coronal mass ejections. The structure of the wind at the moment of launch can dramatically affect the speed, density, and geomagnetic impact of an ejection when it eventually arrives at Earth. If the barrier is changing the energy budget of the corona, making it more efficient at trapping certain kinds of energy and releasing it in specific bursts, then it would be naive to assume it has no influence on the eruptions that emerge from that environment. This is the kind of question that takes years to answer. It requires comparing thousands of Parker measurements to thousands of Earth-side geomagnetic records. It requires building new models that incorporate the barrier into the physics. It requires waiting for the next cycle, and the one after that, to see if the patterns hold. But the question has been asked, and it is now driving some of the most urgent research happening at NASA, ESA, and dozens of universities around the world. In the meantime, Parker keeps flying. Its next close approach is already scheduled. Its instruments are already pointed inward. And every pass brings back more data than the entire previous decade of solar observation combined. It's important, in a story this large, to acknowledge that not everyone agrees on what Parker has actually found. Some physicists argue that the Helicity Barrier, while real, is being overinterpreted. They argue that it is one of several mechanisms operating in the corona, and that singling it out as the dominant heating process is premature. They point out that turbulence, wave heating, and nanoflares may all still play significant roles, and that the truth of coronal heating is almost certainly multiple processes operating in concert. Other researchers argue something more cautious. They argue that what Parker measured is a real signal, but that the interpretation depends heavily on the specific assumptions baked into the analysis. Change the assumptions, they say, and the barrier looks different, maybe even disappears. These are not fringe critiques, They are the normal, healthy disagreements of a scientific community working at the edge of what is known. But there is also a third interpretation, a more unsettling one. A small number of researchers, and you can find their work in the public literature if you go looking, argue that what Parker is detecting in the corona is even stranger than the barrier itself. They argue that the corona may be exhibiting behaviours that don't fit any known turbulence model, that the energy cascade is being interrupted in ways that suggest physics we don't fully understand yet. This is not pseudoscience. This is published work in respected journals by serious researchers. But it carries an undertone that makes some in the field uncomfortable. Because if it's right, then the sun is doing something inside its own atmosphere that is, on a fundamental level, new physics. And if new physics is operating 3.8 million miles from Earth physics we did not predict, physics our models cannot reproduce, physics that influences the energy and matter the sun throws at our planet, then the honest answer to the question of what is happening up there is that we still do not fully know. We just have a probe inside the storm, sending back data faster than we can interpret it. And the storm is getting louder. NASA's official position is measured. The mission, in their words, is succeeding beyond expectations. The data is being processed, papers are being published. The mystery of coronal heating is being unravelled, piece by piece. That is true. The Johns Hopkins Applied Physics Laboratory, which operates the spacecraft, has issued steady, careful updates after every close approach. They confirm the spacecraft is healthy. They confirm the data is good. They confirm the science is progressing. NOAA's Space Weather Prediction Center continues to issue real-time forecasts for solar activity. Their messaging has been transparent. Solar cycle 25 is in its maximum phase. Activity is elevated. Coronal mass ejections are more frequent. Geomagnetic storms are more likely. Operators of critical infrastructure should be prepared. The European Space Agency has been similarly direct. Their simulation of a Carrington-scale event, a solar superstorm on the scale of the 1859 event that famously set telegraph offices on fire, was released to make clear what the worst case actually looks like. Not to alarm, to prepare. This is the official picture. Careful, confident, methodical. But there is a quieter conversation happening in the scientific literature. A conversation that doesn't make it into press releases. A conversation about how much we still don't understand about the star at the centre of our solar system, and how much that gap matters now that our civilization depends on infrastructure the sun can disable in hours. That conversation is not hidden. It is in plain sight for anyone who reads the papers. But it is not the conversation most people hear. Imagine, for a moment, the May 2024 storm. Imagine the auroras. Imagine the satellites SpaceX lost. Imagine the moments when grid operators in North America watched their voltage readings spike. Imagine the airline pilots who saw their high-frequency radios go silent over the polar routes. Now imagine that storm 5 times stronger. Or 10 times. That is the scale of a Carrington-class event. A storm that, in 1859, made compass needles spin uncontrollably, set fire to telegraph paper, and produced auroras visible from the Caribbean. A storm that, if it hit modern Earth, would cause a level of damage that is genuinely hard to quantify. Estimates from insurance industry analysts and academic researchers vary widely. The most cited figure from a Lloyd's of London report suggests a Carrington-level storm could cause economic damage measured in trillions of dollars. Transformers would be destroyed, power grids would go dark, satellites would be lost, global positioning systems would be degraded for days, aviation would be grounded across polar routes, communications would be disrupted. Modern civilization runs on electricity and on signals from space. Both can be taken from us by the sun. This is not a fringe concern. It is acknowledged by every major space agency on Earth. The question is not if such a storm will happen again. The question is when. And what Parker Solar Probe is teaching us by flying inside the corona and measuring what is actually happening there, is that our understanding of the conditions that produce those storms is still incomplete. The Helicity Barrier is one piece of that puzzle. It may not be the final answer, but it is, undeniably, a piece we did not have before. Which leaves us with a question no one, not NASA, not NOAA, not the most experienced solar physicists alive can answer with certainty. When the next big one comes, will we see it coming in time? Parker Solar Probe is not done. The mission is funded through at least 2026, and there is active discussion within NASA about extending it further. The spacecraft is healthy, the instruments are operating, and there are more close approaches scheduled. Each one will return data that will be analysed for years. Each one has the potential to reveal something new. The Helicity Barrier, the U-turn in the solar wind, the switchbacks, the magnetically dominated regions of the corona, all of these are puzzle pieces that scientists are still fitting together. Beyond Parker, there is Solar Orbiter, the European Space Agency's complementary mission, which is taking high-resolution images of the Sun from a different vantage point. There is the Daniel K. Inouye Solar Telescope in Hawaii, which is now producing the sharpest images of the Sun ever taken from the ground. There is NOAA's GOES satellite fleet, monitoring the Sun in real time. There is the planned Vigil mission from ESA, which will eventually give us advance warning of Earth-directed coronal mass ejections by parking a spacecraft at Lagrange Point 5. The infrastructure to understand the Sun better is being built right now, but the Sun is not waiting for us to finish. In the coming months, watch for any official statement from NOAA's Space Weather Prediction Center regarding a G4 or G5 geomagnetic storm warning. Watch for any reports of large coronal mass ejections from active regions on the Earth facing side of the Sun. Watch for any announcement from NASA about Parker Solar Probe data that contradicts previous assumptions about how the corona behaves. Because the next chapter in this story will not be a paper in a journal. It will not be a press release. It will be an event. If you are watching this and you have your own perspective, if you have read the original Parker Solar Probe research, if you work in space weather, if you remember the May 2024 auroras, tell me in the comments. The conversation matters. The audience that watches these videos is more thoughtful than the algorithm gives credit for, and the comments under videos like this one are often where the most interesting questions get asked. I read them, and they shape what we cover next. There is something philosophically strange about all of this. For most of human history, the Sun was the most familiar object in the sky. It rose, it set, it defined the day, it gave us warmth and food and time itself. Cultures from every continent built their religions around it, their calendars, their stories. The Sun was the constant. The Sun was certainty. And yet, for all of that intimacy, we never really understood it. We told ourselves we did. The Greeks, the Egyptians, the early astronomers of the Enlightenment. Each generation believed it had finally cracked the central star, and each generation was wrong. Even now, in an era of supercomputers, space telescopes and probes inside the corona itself, we are still discovering that the Sun behaves in ways we did not predict, that its atmosphere contains barriers we did not anticipate, that the energy it sends to us is shaped by physics we are still trying to write down. There is a humility in that. But there is also a warning, because the gap between what we know about the Sun and what the Sun is actually doing is not just an academic curiosity. It is the gap inside which space weather happens. It is the gap inside which our power grids, our satellites, and our civilization itself are exposed. Parker Solar Probe is closing that gap. The Helicity Barrier is one of the things it has revealed. There will be more, and in the meantime, we live, as we have always lived, under a star we do not fully understand. It is easy when you spend enough time studying the Sun to start seeing it differently. Most people look at it and see something simple: a ball of fire, a source of light, a predictable, unchanging fixture of the sky. But the Sun is not simple. It is not predictable. It is not unchanging. It is a churning, magnetized, plasma-filled engine of stellar violence, 93 million miles from your front door, whose atmosphere we are only now beginning to map from the inside. It is the most studied object in human history, and it is still surprising the people who have spent their lives studying it. What Parker Solar Probe found in those quiet hours when it slipped through the corona at 500,000 miles per hour was not a comforting answer. It was not a closed book. It was not a mystery solved. It was a barrier. Inside the sun. A barrier that should not exist according to the models we built for half a century. A barrier that traps energy in ways we are still trying to understand. A barrier that may be shaping, in ways we have not yet measured, the storms that will eventually reach our planet. The mission is not over. The next close approach is already on the calendar. The next set of measurements is already being prepared. The next paper is already being written. And somewhere, in the data Parker has not yet transmitted, in the readings it has not yet taken, in the measurements that will arrive in the months and years ahead, there is almost certainly another discovery waiting. Another piece of the sun that does not behave the way we expected. Another quiet revelation that will force us to rewrite something we thought we knew. The sun is not done with us.